Hello everyone, welcome back to another Watch Me Do Math video. In this video I'm going to be going over simple harmonic motion, which is a specific type of motion, a physics system that one can investigate, that is based off one rule. And through a lot of maths, a lot of interesting properties of this motion can be found out just from that particular rule. So, what rule is it that defines simple harmonic motion? Well, for any body in simple harmonic motion, say this block, I would like pink, please. For any body in simple harmonic motion, say this block, there is a particular equilibrium position, x, that it exists, that it will be at rest at forever if it is left there. For instance, this might refer to the equilibrium position of a mass hanging off a string, where mg is equal to the restoring force of the string pulling the mass back upwards, kx minus kx. Or it could be a situation where you've got the mass in a pool of liquid such that it is displacing an equal mass of water, giving the weight force is equal to mg upwards, and leaving the mass equilibrium. So that's what equilibrium means in simple harmonic motion. It's basically an object needs to have an equilibrium for a simple harmonic motion to be possible. But that's not all that defines it, because the reason I've particularly chosen these two systems of for instance, a block submerged in water and a block on the end of a spring, or any mass on the end of a spring, is that there are particular rules in these systems that allow us to consider them examples of simple harmonic motion, assuming no drag, and no friction. So a mass spring system, which is a common thing to be studied with simple harmonic motion, is going to be a better example of simple harmonic motion, or SHM as I'm going to call it from now on. And as you might see a lot, it's a better example of SHM than this here, this block bobbing up and down on the water. I investigated this for my physics IA, or I am still investigating it, in fact, and of course I will need to look at the real forces of drag acting on this body, but for this example, we're just looking at simple harmonic motion as a whole. We will not have to. But for the time being, we're going to focus on the mass spring system as it's more realistic. And we're going to figure out some other systems that follow simple harmonic motion later on. So anyway, let's see what else I mean by simple harmonic motion. We've established that objects must have an equilibrium position. And okay, so what does harmonic mean? Well, harmonic might lead you to think of music or sound waves, and that's the key, waves. The simple harmonic motion involves all kinds of graphs that look like this, because the bodies undergoing SHM will oscillate to and fro in a repeating and predictable way. So this is pretty good because it lets us think of SHM in a clearer way. Because a way to describe this kind of oscillating motion is by letting the force, or what I'm going to call the restoring force, on the body back to equilibrium when it's displaced from equilibrium, like a ball at the bottom of a ramp shaped like this. If the ball is displaced from equilibrium this way, then there'll be a larger force on it, and if the ball is displaced from equilibrium this way, then there'll be a larger force on it in both cases towards the equilibrium. So for instance, this ball tries to move anywhere, it will be pushed back to its resting position naturally. So, firstly, we have the concept of an equilibrium. We have the fact that the bodies experience a force towards the equilibrium position. And finally, what last thing defines simple harmonic motion? Well, the reason that simple harmonic motion is what it is, and it's not some other kind of cyclical motion that is not easy to handle, is because the forces involved are proportional to the displacement of a body away from the equilibrium position. So for instance, with a spring, if you think of Hooke's law, the force is proportional to the extension of the spring. If the body is in equilibrium here, and it is pulled x centimeters down, there will be an additional unbalanced restoring force, kx, of kx back towards the equilibrium point. So if this block is pulled down here, a distance x away, there'll be a restoring force of kx newtons, where k is the spring constant, and that is going to be beyond the scope of this video to teach, where k is the spring constant, that determines how much extension begets how much additional force. So while the upwards force may have been mg before, the upwards force is now mg plus kx, while the downwards force is still mg, it's the weight of the block. And so the block experiences a resultant force, kx, when it is displaced by x away from the equilibrium position. And you could also look at it in the sense that when the block is above the equilibrium by kx, the spring is pulling on the block with a force of kx less than mg, than the block's weight. And so it experiences that same force, kx, if the block is up here and it's x away from the equilibrium, the block experiences the same force, kx, but downwards. And so we get that this force is equal to this force is equal to minus kx. The significance of the minus sign here is that it's in the opposite direction of the displacement, x, which really should be treated as a vector. So the force vector is equal to the negative of the displacement vector multiplied by some constant, which I'm going to call k here. So that's sort of the physics section of this video. That's the logic behind simple harmonic motion and the rules that describe it. Now we're going to get quite deep into the weeds of mathematics to solve this simple system that we've created, this one equation. The force vector is equal to the displacement vector in the opposite direction. So remember, if the mass is displaced like this, then the force is like this, opposite direction, so minus sign. The opposite direction of the displacement vector multiplied by some constant k, where k in the case of the spring and the mass is the spring constant of that spring, but k in this scenario can take anything because it's a constant of proportionality. In fact, you could rewrite this rule as the force vector is proportional to the negative of the displacement vector. Cool. So, what now? Well, if we go back to Newton's second law, F is equal to ma, there's no need for me to say the whole second law out because this describes it. Then we get an equation that can be solved for the acceleration of the body. Because if we stop looking at the forces here, it becomes easier to think of the body's motion in just a sense of motion, displacement, velocity, acceleration, so on. Forces are completely removed from the equation after this point. So if F is equal to ma, then we could also write this as the net force vector, the resultant force vector is equal to the mass of the body times the acceleration vector, or really the acceleration vector is equal to the force vector divided by the mass, because I'd prefer to write it in this form since it's the force that's causing the acceleration, and how much acceleration it causes is controlled by the mass. So this makes more sense in my head than F is equal to ma, even though this is easier to remember. Acceleration vector is equal to the force vector divided by the mass, and so, or F is equal to ma, and so we get ma is equal to minus the displacement, the negative of the displacement, times k, which is the spring constant, or some constant of proportionality. So where to go from here? Well, I'm going to take some steps to simplify this problem into a form where we can begin to use calculus to solve this system for things like a function of displacement with time as input, a function of velocity with time as input, a function of velocity with displacement as input, and a function of acceleration with time as input, because the function of displacement with displacement as input is trivial, it's the same thing, and the function of acceleration with displacement as input is already described by this equation. So we're going to look for these four. And these four equations relate the stuff in the information that can be deduced about a body in SHM, in simple harmonic motion, in a convenient way for us. So if mass times acceleration is the negative of the displacement vector times some constant, we can still write that the acceleration is proportional to the opposite of the displacement. Or in other words, the acceleration is equal to minus some constant, which we'll call k again for convenience. This is not the spring constant. This is not the spring constant. Do not treat it like the same thing. This is just convenient. A is equal to minus k times, you know what, I'm actually just going to use a different letter than the spring constant just to make it clear. So A is equal to minus bx, where capital B is some constant that we're dealing with in the system that is dependent on the parameters of the system, because this equation describes all of simple harmonic motion and not just the mass and spring system. This is like the equation that defines it all, the equation that started it all, and the equation from which we can derive everything involved. So I'm going to clear the board now, and we're going to get into a mathematical mindset where we're going to analyze this equation for those functions xt, vt, at, and vx, as I said before. Right, so if I just go up to the corner here and write it down again, a is equal to minus bx. So where should we start? Well, we know that a is related to x in some way. And how do we know that? Well, through kinematics, where the study of displacement, velocity, acceleration, and so on. By the way, if you haven't already, please do subscribe because I forgot to mention this earlier in the video. The acceleration is equal to minus b times x, where b is some constant. But this is not that important to us because through what we remember from kinematics, we know that acceleration is the second differential of displacement with respect to time. Or in other words, acceleration is the rate of change of displacement with respect to time So it's like if velocity is dx by dt, and acceleration is dv by dt, and then acceleration is d of dx by dt by dt, which we tend to write as d squared x over dt squared, which is probably the notation you saw being used for this kind of thing before. So d squared x divided by dt squared is a. But we're actually going to go back and look at it from the perspective of this dv by dt here. A is equal to minus bx, as you might have expected from the title. We're going to be using dv by dt in a pretty unique way to tackle the problem. dv by dt is therefore equal to minus bx, because this is a, right? So if we multiply dv by dt by dx over dx, which is equal to 1, we're not actually changing anything in the equation, are we? So dv by dt multiplied by dx over dx is equal to minus bx. Now here's the interesting thing. dv, dt, and dx all are individual things that we can think about. That they represent a infinitely small change in some quantity, x, t, or v. They're not mathematical concepts that, well, I mean they are, but they can't be treated in this scenario at least as if this is one object. There's a reason we write it like this, dv by dt, because in the physics world we are allowed to do things like move these terms around as if dv by dt were a fraction. In the most pure, strict mathematical sense, that's not really the case. However, we can treat it like this for the purposes of problem solving. So if we swap dx and dt on the bottom here, because this is really telling us dv multiplied by dx is equal to over dt multiplied by dx is equal to minus bx, we can rewrite these two fractions as dv by dx times dx by dt is equal to minus bx. And since v is dx by dt, as we learned in my kinematics video earlier, or just in your studies somewhere, we can make this substitution and write dv by dx is equal to times v is equal to minus bx. And you see how we transform this term into the symbol v. So what next? dv by dx times v is equal to minus bx. we have here a differential equation in terms of v and x. So what we can do, because it's separable, we can multiply both sides by dx to get something in terms of v and dv on one side, and something in terms of x and dx on the other side. We're going to do exactly that. If you want to know more about the intuition behind solving differential equations like this, then do look at my video on differential equations with year 11 math about the Newton's law of cooling. So anyway, we write v dv by dx is equal to minus bx. Multiplying both sides by dx, we get v dv is equal to minus bx dx. Now, technically, mathematically speaking, in the strictest possible sense, we are only writing here 0 is equal to 0. But in the physics sense, these are meaningful things. This refers to an infinitesimal change in dx, and this refers to an infinitesimal change in dv. And they're related by this ratio dv by dx that we've shown earlier. So, given that these are both infinitesimal things here, we can make them into reasonably sized things, like reasonably sized numbers that are not 0, through the process of integration, the continuous summing. So the sum of all the v's times the infinitesimal change in v dv must be equal to the sum of all the infinitesimal change in x's dx times minus bx. Or in other words, replacing sum with this ridiculously large s drawn on purpose to symbolize the integral sign, the integral of v dv must therefore be equal to the integral of minus bx dx. So integrating one side, we have the integral of v dv is 1 over 2v squared plus c, and the integral of minus bx dx is minus b over 2 x squared. And we're just going to multiply everything by 2 for convenience, so v squared plus c, this is an arbitrary constant and it doesn't really matter that much to us. V squared plus c is equal to minus b x squared, or v is equal to root c minus bx squared. So how might we find what c is in this scenario? And by the way, you may notice that this is positive c on this side and a positive c on this side. Even though I minused c, even though I subtracted c, that still brings us another unknown constant term on the right-hand side. So I decided to leave it in the form c. Basically, anything that you can do to a constant that would continue to make it a constant, just write c in, unless you are paying particular attention to that constant, which we are indeed doing with b. So if v is equal to the square root of c minus bx squared, well, one thing to remember is that when we look at simple harmonic motion, we're looking at something which has a particular amplitude. If it takes a certain amount of energy to compress a spring by x centimeters, and the mass in the system is only charged with that much energy, charged not being the accurate term here, but anyway, you get what I mean. The mass only has so much internal energy in the form of kinetic energy when it's moving its fastest, in its sort of displacement is equal to the equilibrium position, because there is no potential energy for the particle there, as if it were to move either side of the equilibrium, it would need to convert kinetic energy into potential energy. That's why it is the equilibrium in the first place, right? As the particle moves up one cycle, when it reaches the top of this displacement time graph that you see here, well, the gradient is 0. The body is momentarily stationary, meaning that it has no kinetic energy or no velocity, all potential energy, when x is equal to the amplitude. And in the IB at least, we call this amplitude x0. So knowing that v is equal to 0 when x is equal to x0, 0 is equal to the square root of c minus bx squared. Well, given that x is x0, this is c minus bx0 squared. And let's move on and find that squaring both sides, we get 0 is equal to c minus bx0 squared, or that c is equal to bx0 squared. Adding bx0 squared to both sides and swapping the equation's direction around. So this constant integration c is equal to bx0 squared. And that leads us to one of the formulas that I said we'd find in the beginning, v in terms of x, because this v is equal to c minus bx squared now has a complete meaning for us, that v is equal to the square root of bx0 squared minus x squared, or rather v is equal to minus bx squared. V is equal to root b times the square root of x naught squared, the amplitude squared, minus x squared, the displacement squared, right? So that was pretty mathematically rigorous, and you might be best served going back and pausing and making sure that you can follow along. But anyway, yeah, that's the information that is needed here to get from a is equal to minus bx to this right here, right? Okay, so now let's charge ahead. V is equal to dx by dt. Well, this is one formula, right? Now we must consider that v is equal to dx by dt. Here we have another differential equation. Who would have guessed? So, given that this is a separable differential equation, and we can separate the dx and the dt, that's what I mean by separable. And it's a differential equation because we've got a differential on one side and some terms on the other side. I'm going to multiply both sides by dt, such that we know that dx, the infinitesimal change in x at any x, is equal to this constant, the square root of b, times x naught squared minus x squared. Well, naught is a form of saying 0. X naught squared minus x squared multiplied by the infinitesimal change in time dt. Dx is equal to that dt. And if we integrate both sides of this now, we won't be able to, because this is in terms of x and we'd be integrating by with respect to t. So I'm going to divide both sides by this square root term to get 1 over x naught squared minus x squared. And by the way, you can think of this like the proportion of the maximum velocity, because Vmax is going to be when x is equal to 0, or Vmax is going to be equal to root b x0, because x squared is going to be, x squared is 0 when that term is at its maximum, right? So you can think of this particular square root as like the proportion of v max that the body is currently moving at. If v max was 1, it would be like, oh, we're at 50% speed because this square root is at 0.5 value. Anyway, that's a bit of a side note. 1 over that square root term multiplied by the infinitesimal change in x dx is equal to dt. And if we integrate both sides now for it's equal to the square root of b times dt. And if we now, for real, integrate both sides, we get the integral of 1 over that square root term is equal to the integral of root b dt. And this integral I'm just going to do in one fell swoop because I already know that this is arc sine x over x0. And if you are wondering how I reached that, please see part 0, episode 0 of this series. Arc sine x over x0 is equal to root b t plus c, where c is our constant of integration. Or, in other words, solving this equation for something in terms of t, knowing that arc sine x over x0, where x0 is our amplitude of the motion, is equal to root b t plus c. We take the sine of both sides, sine of arc sine x over x0 is equal to sine of the right-hand side, and sine of arc sine of anything is the thing inside the arc sine. It's the input to that function. So x over x naught is equal to the sine of root b times t plus c, or x is equal to x naught sine root bt plus c. And if you have learned simple harmonic motion before, this equation is going to look very familiar to you. And honestly, it will be. Naturally, that is the case when you've worked with an equation to such a great extent as you might have in your learning of simple harmonic motion. And this root b and c might look a little out of place to you, so we're going to investigate why the symbols that are used in simple harmonic motion are indeed used. So, say you've got this sine function here. It repeats itself every 2 pi radians. And so this plus c, you might consider it as a sort of phase difference from the normal way a sine function is. For instance, if I had this one sine graph and it started here, then there would be a phase difference of 0 because that's where a sine graph normally starts. But for instance, if I started the graph here, then there'd be a phase difference of pi over 4 radians. And since this is kind of an angle, this term represents an angle pretty much since it's the inside of a sine function, we use the symbol for phase difference of the motion involved. Phase difference meaning, like, basically if you have something that repeats itself, how far along in the repetition is it, and what's the difference between those points. That phase difference is a measure of angle, so we're going to use the symbol for angle, a relevant symbol for angles, which also happens to be the mathematical symbol for phase difference. Psi. I think it's pronounced psi? I'm not sure. Or just psi. Anyway, x is equal to x0 sine root b t plus psi. Now, what else is missing here? This root b. It's a little strange, don't you think? Well, this root b is often called omega because omega, in your study of circular motion, might refer to angular velocity, which is sort of this concept that describes the speed at which something is rotating. And of course, nothing in simple harmonic motion is rotating, but if you looked at a object moving in simple harmonic motion head-on, like this, so it's moving up and down, and at the same time you had, for instance, a circle that was continuously spinning, a circular disk that's spinning, with some marker on it, on the outside, and you set them off at the same time, can you see with how the elevation of the unit circle at a particular angle theta is sine theta? Because if angular momentum is the rate at which theta is changing, and therefore the rate this influences the rate at which x is changing, as x is sine of that angle, as in sine theta changes at a rate of cos theta, so sine root vt plus theta plus psi will change at a rate of root b cos root b t plus psi. Wait, actually no. Scrap this. The point is, it's kind of similar to circular motion in the sense that it's only one dimension of circular motion, right? So anyway, this root b is called omega because it is basically the angular momentum of the body involved as it moves through the sine wave. So if it moves through the sine wave at one sine wave at a time, one oscillation, complete oscillation at a time, then it will have an angular velocity of 2 pi, as in 1 second will increase this by 2 pi, demonstrating how the body moves through 2 pi radians of the cycle each time. So x is equal to x naught sine omega, standing for the angular velocity of the mass or body involved, which again, this is not referring to a literal angle in this equation. It's still the concept that, as you can probably tell, I'm wrapping my head around. This instead refers to how far or how fast something moves along a sine wave, or how fast the displacement moves along a sine wave. X is going to be equal to x0, the amplitude, times sine of omega t plus psi, the phase difference. And from here, it's pretty trivial to find v and a in terms of t, because they are just the differentials of x0 sine omega t plus psi with respect to t. So let's just work those out momentarily. V is equal to x0 times, letting u is equal to omega t plus psi. U prime differentiated with respect to t is just omega. So we multiply that by whatever the differential of this in terms of u is. So by the chain rule, velocity must be x naught times omega cos omega t plus psi, and acceleration must be x naught omega squared, or minus x naught omega squared omega t plus psi, and through two roots, either in the sense that omega is equal to square root of b and therefore b is equal to omega squared, that's one root, or in dividing a over x, Cancelling these terms, you can find that our original constant of proportionality that we were messing with, b, is equal to omega squared, the square of the angular velocity of the whole system, which is a pretty neat result. So I know these three equations were a bit rushed, but it's only differentiation with respect to t. The hardest part of this whole thing was probably just explaining the physics behind it, because there's a lot of base knowledge that you might need in order to understand what I'm talking about due to the amount of terminology involved with simple harmonic motion. But either way, I hope that this video was helpful to you, and that it to you as an IB or even ambitious IGCSE student was able to understand the concept at least partially, or review it from this video. So, thank you for watching. And do subscribe if this helped you. Leave a comment, or email watchmedomath@gmail.com if you have a request. Goodbye.